Going on now to Chapter 3, Exponential and Logarithmic Functions. Topic 1, Exponential Functions. Now, here are the objectives. Evaluate exponential functions, graph exponential functions, evaluate functions with base e, and then using compound interest formula. As we start our notes now, we want to take a look at what is the basic form of our exponential function. Well, it's f of x equals our base, b, to some exponent, which we will call x. Or, again, you can replace the f of x with a y. Now, b is a positive constant other than 1. You cannot have 1 as a base. And b needs to be greater than 0. And b cannot be a 1. And x then is any real number. That could be negative or positive. All right, some parameters. Let's go on. Now for example 1, and you want to include that in your notes, the exponential function is given here. Models the average amount spent in dollars at a shopping mall after this many hours. So our value for x is going to be number of hours. What is the average amount spent to the nearest dollar after 3 hours at the shopping mall? So we're going to substitute the 3 for the x that we see here. So take a moment. Now write this down. You're going to put this in your calculator. It gives you this approximation, which we're going to round now to the nearest dollar. And we go here to the cents, and this is, in a sense, 20 cents. So the nearest dollar would be 160. Now, in example 2, we're asked to sketch this graph. So let's put it on our whiteboard. F of x equals 3 to the x power. So we get something that looks like this. Now, if our base is 3 and x is 0, 3 to the 0 power, or anything to the 0 power, is 1. If our exponent is 1, 3 to the first power is 3. 2 for our x value, that would be 3 to the second power is 9. Now, when we have a negative exponent, it's just the reciprocal of what we have here. So 3 to the negative 1 is the reciprocal of 3, which is 1/3. And 3 to the negative 2 is the reciprocal of 9, which is 1/9. Now, when we plot this, x to the 0 power is 1. We get a dot there. 1, we get a dot there. And then if we had x is 2, comes up to 9, which is about there. And then negative 1 is about 1/3. And then about 1/9. And then it would be 1/27th. And this would be 27 out there. So we get a curve then. And I'm just kind of sketching this here. that looks like that. Now, this gets closer and closer as the fractions get smaller and smaller and smaller to the x-axis, but never reaches the x-axis. We're going to talk about that a little bit later. So while we're here, let's do our domain. And this will go to negative infinity and continues to move ever so slowly in this direction, but to positive infinity. Now the range never reaches zero. So our y value is, we start at zero, but it doesn't reach zero. That's why we have the parenthesis. And it goes to positive infinity. Now let's take a look at the graph that's there. Now here we see the nice smooth graph when you have the proper tools to do it. Going on to our next slide. This is the characteristics of exponential functions. Now there's our basic form. And here they're showing, and if our b value for the blue line is greater than 1, it'll have this basic shape where it starts low and then rises as you go to the left. Now if b is less than 1 but greater than 0, this would be some sort of fraction. It's going to start high on the left and then go in this direction. But remember, whenever the exponent is 0, it's going to go through 1. Now, we mentioned that the x-axis is what this line gets close to, but never reaches. A line that something gets close to but never reaches is called an asymptote. You want to be sure to have that word down. And since it's a horizontal line, the x-axis is called the horizontal asymptote. And you may recall from an earlier lesson, what is the equation of a line that's horizontal and goes through 0 on the y-axis? Well, that is a horizontal line, y equals 0. And that's what they're saying. Now, it's kind of a tad confusing thinking that the x-axis equation is y equals 0, but that's what it is. All right, let's go on. Now, in example 3, they're asking us to show transformation involving an exponential function. So on the previous slide, we saw what this looked like. But now we're going to put the graph of 3 exponent, and in a sense this should be in a parenthesis, x minus 1. So there's our original. And now let's take a look at its transformation. And this slide explains it very well. Let's see if we can follow. So there's our original, and that's the black line. The graph will shift 1 unit to the right. Now remember, we said in things like this, where you might say, well, it's going to shift 1 unit to the left because negative 1. No, we add 1 when this is a negative 1 to each of the coordinates. So for where it was 0, 1, it's going to move over 1 and now in this position. And then 0, 2, it's going to go over 1 to 2 now, and then up there. All right. And notice where it was a -1 was a 1/3. That's going to shift over now to the y-axis at 1/3. Now our x-axis is still the horizontal asymptote with the equation y equals 0. Now in this next slide, we're going to look at what is referred to as the natural base, which is the letter E. This was named after Euler, although he didn't claim it. He's the one that developed it, and its value results from expanding this, which we're not going to go into here. But as this gets larger and larger, it approaches infinity. The approximate value of this, and I see we have some extra marks here, is what we see here. It's often rounded off to 2 decimal places, where we go to the third, which is an 8, so it makes this 1 a 2. Now, when we see it in this form, the function of x is equal to e to the x power. This is referred to as the natural exponential function. And we use that e in many mathematical processes that we'll see later as we progress. So in example 4, we have this function in which they're using the letter E, which models the gray wolf population after these many years and recovering in that. Now, because this 2012 is 34 years after 1978, we substitute this 34 for the letter X. So now this is just being able to put this into your calculator. You put 1066 and then times E caret, and some of the calculators have the caret built in, so you have to know how to use your instrument. And then I would put all of this in parentheses, 0.042 times, just hit the times key, 34, close the parenthesis, hit enter, and it gives you this rounded off to the nearest whole number. Again, you have to be careful, can't have part of a wolf, so you have to have it whole numbers here, yes. All right, let's go on. As we talk about exponential functions, 2 formulas come into play. One is the compound interest formula per year, and then we have another one in which we have continuous compounding. So let's go through the items in the formula. A is the same in both. This refers to the future amount. P is the same in both, which is your amount of initial money. We call it the principal that you're starting off with. And then there's 1, which is straightforward, plus R, which is the rate, which is a percentage that we convert to a decimal fraction. And then n refers to the number of times something is compounded during the year. So if it's annually, that would be once. Semi-annually, that would be twice. Quarterly, that would be 4 times. Monthly, that would be 12 times. Then we have daily, which would be 365. And then you could have others, but just think that if you're compounding the money that you have put in and it becomes, let's say, hourly, that number gets bigger, and then seconds, and then tenths of seconds, and then eventually continuously, that's where you get to this formula, and you use Euler's E there. But now the exponent is to the rate times the number of years. So again, using this and then tying it in with your homework will be a very useful thing. Let's go on to an example. So here, a sum of 10,000 is invested at an annual rate of 8%. Find the balance, that is the future amount, after 5 years. And we're compounding it quarterly. So A is our future amount. Our principal is 10,000. 1 plus our rate is 8% that we convert to a decimal fraction. Our n is the number of times it's compounded during the year, which is 4. And then our exponent is going to be our n again, which is 4, times the number of years, which is 5. So this here is going to end up being 20. Now again, I would do this division first, add 1 to it, get the exponent 20, then multiply it by 10,000, and it ends up with this. Not a bad investment, and rate of interest being 8%, that's really very, very good. Now, for our last slide, example 5, we're going to invest this, but it's subject to continuous compounding interest. Okay, so there's our different formula. Our principal is the same, but now we're using Euler's E. And again, caret, can put this in parentheses, 0.08 times 5 in a parenthesis. Hit enter, and you get this. Now, notice what we had in the previous slide, and we'll compare it. So this is $14,918.25. Let's go back to the earlier slide. And you can see with continuous compounding interest using Euler's E, the value is more. And again, compound interest in reflection is your principal is increasing as you add the interest you've earned for that period of time. All right, let's close this up here.